The moon is not what you think it is. For over 50 years, we've told ourselves a comfortable story. We went, we conquered, we moved on to bigger things. 6 landings, 12 men, a few hundred kilograms of rocks, and then silence. Half a century of silence. The explanation most people accept is tidy. Budget cuts, shifting priorities. Been there, done that. That explanation is a lie we tell ourselves because the truth is harder to swallow. The real reason we haven't been back to the moon is that going back is harder than going the first time, and almost nobody wants to say that out loud. Apollo was not a space program. It was a political weapon aimed at Moscow, funded like a wartime mobilization, and executed with a tolerance for risk that would end careers and trigger congressional investigations today. The astronauts knew the odds. Some of them wrote letters to their families before launch, letters meant to be opened in the event they didn't come home. NASA's own internal estimates during the early Gemini and Apollo years put the probability of a fatal crew loss on any given mission somewhere between 1 in 4 and 1 in 10, depending on who was doing the math and how honest they were being. Those aren't engineering margins. Those are gambling odds. And America was willing to gamble because losing the moon to the Soviet Union felt, in the corridors of power, like losing the Cold War itself. So we sprinted. And sprinting worked exactly once. The Saturn V rocket remains the most powerful machine humanity has ever built. 110 meters tall, producing 34.5 million newtons of thrust at liftoff, burning through roughly 770,000 liters of kerosene and 1.2 million liters of liquid oxygen in the first 2.5 minutes of flight alone. 13 Saturn V's flew between 1967 and 1973. None experienced a catastrophic failure. That record looks like engineering perfection, and in many ways it was. But it was also statistical luck, layered on top of meticulous craftsmanship. The margins were thin. The consequences of any single valve failure, turbopump anomaly, or guidance error were absolute. Each Saturn V cost roughly $1.6 billion in today's money. Each one was used once and thrown into the ocean or left to drift in solar orbit. The entire vehicle, 3 stages, 5 first-stage engines, 5 second-stage engines, 1 third-stage engine, the instrument unit, the launch escape system. All of it was expendable. You built it, you flew it, it was gone. The economics of that approach only work when a superpower is writing blank checks, and by 1970, the checks had stopped. Richard Nixon wanted the money for Vietnam. Congress wanted it for domestic programs. The public, which had watched the moon landings with genuine wonder, had moved on with startling speed. Apollo 13's near disaster in April 1970 briefly rekindled attention, but the subsequent missions, Apollo 14 through 17, drew steadily smaller television audiences. By the time Gene Cernan stepped off the lunar surface on December 14, 1972, most Americans couldn't name the crew. The country had collectively decided that the moon was finished. And there is a detail from Apollo 17 that rarely gets mentioned, but that I think captures the whole tragedy of what came next. The original Apollo program had planned for missions through Apollo 20. 3 more landings, 3 more crews, 3 more chances to explore different terrain, collect different samples, answer different questions. Apollo 18 would have visited Copernicus crater. Apollo 19 was slated for Hadley Rilla, though some proposals targeted the Hyginus region. Apollo 20 was penciled in for a site in the lunar highlands that would have provided the oldest crustal samples ever collected. All three were cancelled before they flew, not because of technical failure, not because of danger, but because Congress cut the funding and NASA needed the Saturn V hardware for Skylab. The rockets that would have carried 3 more crews to the moon were repurposed or put in museums. You can see one of them right now, lying on its side at the Johnson Space Center in Houston, a 110-meter monument to a future that got canceled. What happened next is the part nobody talks about, and it's the part that matters most. The infrastructure didn't just go dormant, it was actively destroyed. The Saturn V production line at the Michoud Assembly Facility in New Orleans was shut down and repurposed. The tooling, the jigs, the specialized fixtures that shaped those massive fuel tanks, gone, not stored, not mothballed, scrapped. The assembly buildings at Kennedy Space Center were reconfigured for the space shuttle, which was a fundamentally different vehicle, with fundamentally different requirements. The supply chain that fed the Apollo program, thousands of subcontractors across dozens of states, producing thousands of unique components, dissolved into the broader aerospace industry. Within 5 years of the last moon landing, the United States lacked the physical capability to build another Saturn V, even if it had wanted to. But the hardware was only half the loss. The other half was the people. Building a rocket to the moon requires an army, not just the headline names, not just Wernher von Braun and the astronauts, but tens of thousands of engineers, machinists, welders, technicians, quality inspectors, and systems integrators working in concert across hundreds of organizations. These people carried institutional knowledge that existed nowhere on paper. How to weld the seams on a fuel tank to tolerances measured in thousandths of an inch. How to diagnose a combustion instability in an F1 engine by the sound it made during a test firing. How to route cabling through the instrument unit so that electromagnetic interference from one system didn't corrupt another. This wasn't textbook knowledge. It was craft knowledge, earned through years of practice and failure, and it lived exclusively in the hands and minds of the people who did the work. When Apollo ended, those people scattered. Some moved to the shuttle program. Some left aerospace entirely. Some retired. And crucially, many of them never trained successors because there was no program to succeed to. By the 1990s, a significant portion of that workforce was in their 60s and 70s. By the 2010s, many were dead. The knowledge went with them. This is the problem that people outside the aerospace industry consistently underestimate. You cannot Google your way to the moon. You cannot reconstruct the operational expertise of 100,000 specialists from archived blueprints and technical reports. Building a moon rocket is not like building a car where you can hire new workers, hand them a manual, and start the line. It is more like trying to recreate a lost culinary tradition by reading the recipe without ever having tasted the dish. The recipe tells you the ingredients. It does not teach you the feel of the dough under your hands, the sound the oil makes when it's at the right temperature, the instinct for when something is about to go wrong. NASA learned this lesson the hard way when it tried to restart large-scale rocket development. The Constellation program began in 2005 under President George W. Bush, born from a directive called the Vision for Space Exploration that was itself born from grief. The Columbia disaster in February 2003, which killed 7 astronauts when the shuttle broke apart during re-entry, forced a national reckoning with the shuttle program's future. The vehicle was aging. The thermal protection system was known to be vulnerable, and the fundamental design, with the orbiter mounted alongside the external tank rather than on top of it, meant that debris strikes during launch were not a freak accident, but a structural feature of the architecture. Columbia was not bad luck. It was a consequence of design compromises made in the 1970s finally catching up. Bush's directive retired the shuttle and proposed its replacement: the Ares 1 crew launch vehicle, the Ares 5 heavy lift cargo vehicle, and the Orion crew capsule, all pointed at the moon with a target landing date of 2020. On paper, it was elegant. In practice, it was underfunded from its first day. The core problem was that Constellation had to compete for dollars with the International Space Station, which was still being assembled, and which Congress had no intention of abandoning after spending over $100 billion building it. The station ate money. Constellation got the leftovers, and the leftovers were not enough to develop 2 new rockets, a new capsule, and a lunar lander simultaneously. By 2008, the Ares 1 was behind schedule. The Ares 5 existed only as concept drawings. The lunar lander, called Altair, hadn't progressed beyond preliminary design reviews. The Orion capsule was coming along, slowly, but it was the only piece making real progress, and even it was overweight and over budget. The entire program was stretching like taffy, getting thinner every year, without getting any closer to the moon. In 2009, President Obama commissioned a review led by Norm Augustine, a retired Lockheed Martin CEO with deep experience in aerospace policy. The Augustine Committee spent months interviewing engineers, reviewing budgets, and modeling scenarios. Their conclusion was diplomatically phrased, but brutal in substance. Under the current budget profile, Constellation could not return humans to the moon before the late 2020s at the earliest, and even that timeline assumed no further cost growth, no further schedule slips, and no reduction in annual funding. Since all 3 of those assumptions were almost certainly wrong, the committee's real message was simpler: this program, as funded, will never reach the moon. Obama canceled Constellation in February 2010, keeping Orion alive, but killing Ares, and redirecting NASA toward a vague and uninspiring plan to visit an asteroid by 2025. The asteroid mission excited approximately no one, inside or outside the agency. It felt like a consolation prize, a destination chosen not because it was compelling, but because it was cheaper than the moon and less ambitious than Mars. Within a few years, the asteroid redirect mission was itself quietly shelved. What emerged from the wreckage was the Space Launch System. SLS is the most politically engineered rocket in history, and I mean that literally. Its architecture was dictated not by what was optimal for reaching the moon, but by what would preserve the maximum number of shuttle-era contracts and jobs in the maximum number of congressional districts. The solid rocket boosters are built by Northrop Grumman in Promontory, Utah, because the senator from Utah sat on the Appropriations Committee. The RS-25 engines are built by Aerojet Rocketdyne in Stennis, Mississippi, because the senator from Mississippi chaired the Commerce Committee. The core stage is assembled at Michoud in Louisiana, because the entire Louisiana delegation had a vested interest in keeping that facility operational. None of this is secret. None of it is even controversial within the industry. Everyone involved understands the arrangement. The rocket is a jobs program that also goes to space, and as a jobs program, it has been spectacularly successful. As a space vehicle, the results are more complicated. SLS took over a decade to develop. Its first flight, Artemis 1, occurred in November 2022, an uncrewed test mission that sent the Orion capsule on a 25-day trip around the moon. The mission worked. Orion's heat shield handled re-entry at lunar return velocities, which are significantly faster and hotter than returns from low Earth orbit. The service module, built by the European Space Agency, performed well. The SLS core stage and boosters functioned as designed. By any technical measure, Artemis 1 was a success. But the numbers behind that success tell a different story. The total development cost of SLS through its first flight was somewhere between $23 and $27 billion, depending on which components you include in the accounting. Each subsequent launch is estimated at roughly $2.2 billion, and that figure has been climbing. The rocket is fully expendable. Every engine, every booster segment, every fuel tank is destroyed on every flight. NASA has 4 RS-25 engines left over from the shuttle program, enough for one more ECLS flight after Artemis 2. After that, new engines must be manufactured at a cost that Aerojet Rocketdyne has been reluctant to publicly specify, but that industry analysts estimate at $100 million or more per engine. You need 4 per launch. For context, SpaceX's Falcon Heavy can deliver around 64 metric tons to low Earth orbit for approximately $150 million per launch. ACLS delivers roughly 95 metric tons to the same orbit for 15 times the price. And Falcon Heavy, while not reusable in its expendable configuration side boosters, does recover them in its standard configuration. SLS recovers nothing. The economic argument against SLS is not subtle. It is not a matter of interpretation. It is arithmetic. And yet SLS continues because the political architecture that sustains it is more durable than any rocket. I want to pause here because there's something important that gets lost in the budget debates and the political criticism. The engineers who work on SLS are not the problem. They are some of the most talented and dedicated people in aerospace. They have built a rocket that works, that flies, that could carry humans around the moon and bring them home safely. The problem is not the engineering. The problem is that the system surrounding the engineering, the funding model, the contracting structure, the political incentives, produces a vehicle that is too expensive to use frequently enough to matter. A rocket that flies once every 2 years cannot sustain a lunar program. It can only perform occasional demonstrations, and demonstrations are not what the moon requires anymore. The thing that changed the calculus, the thing that transformed the moon from a been-there-done-that destination into a strategic target, was water. For most of the 20th century, the scientific consensus was clear. The moon is bone dry. The Apollo samples confirmed it. Hundreds of kilograms of lunar rock and soil were analyzed in laboratories around the world, and the results were consistent. Trace amounts of hydrogen, yes, but actual water molecules, water ice, anything that could meaningfully be called water? No. The moon was dead, dry, and geologically inert. Case closed. Except the case was built on a flawed assumption that took decades to recognize. Every Apollo landing site was chosen for safety and accessibility, not for scientific diversity. All 6 were clustered in a relatively narrow band near the lunar equator, on the near side, in flat terrain. It was like landing a spaceship in the Sahara Desert and concluding the entire Earth is sand. The Apollo samples were real. The analysis was meticulous, but the sampling was biased from the start. We built a global model from local data and called it complete. The case started reopening in 1994 when the Clementine Orbiter, a joint mission between NASA and the Ballistic Missile Defense Organization, detected what appeared to be anomalous radar reflections from the permanently shadowed craters near the South Pole. The data was ambiguous. Other materials could produce similar radar signatures, but it was intriguing enough to warrant a closer look. That closer look came in 1998 with Lunar Prospector, a small, inexpensive orbiter carrying a neutron spectrometer. The instrument worked by detecting the energy of neutrons bouncing off the lunar surface. When fast neutrons from cosmic rays strike the ground and interact with hydrogen, they lose energy, slowing down measurably. Lunar Prospector found distinct concentrations of slow, epithermal neutrons at both poles, consistent with significant hydrogen deposits in the regolith. The most likely source of that hydrogen was water ice, trapped in the permanently shadowed craters, where temperatures plunge below -230 degrees Celsius, cold enough that ice doesn't sublimate. It just sits there, accumulating over billions of years, delivered by comets and asteroids and solar wind interactions, gram by gram, molecule by molecule. The confirmation became definitive across a series of missions in 2008 and 2009. India's Chandrayaan-1 orbiter carried a NASA instrument called the Moon Mineralogy Mapper, or M3, which detected absorption features at 2.8 to 3 micrometers wavelength on the sunlit surface. That specific absorption band is the spectral fingerprint of water molecules, bonded to minerals or trapped in glass. And it wasn't just at the poles. It was everywhere, diffused across the regolith, concentrated in tiny glass beads formed by the heat of ancient volcanic eruptions and meteorite impacts. The beads act like a sponge, absorbing hydrogen from the solar wind and locking it into their structure. The water is there, spread thinly, but present in quantities that add up. Then came L-Cross. On October 9th, 2009, NASA deliberately slammed a spent Centaur upper stage into Cabeus crater near the South Pole at 9,000 kilometers per hour. A trailing spacecraft flew through the resulting debris plume and analyzed its composition with spectrometers. The plume contained water ice, not trace amounts, not ambiguous signatures, real water ice, approximately 155 kilograms of it from a single impact. Along with it came mercury, magnesium, calcium, silver, carbon dioxide, carbon monoxide, ammonia, and sodium. The permanently shadowed craters weren't just cold. They were cold traps, collecting and preserving volatile compounds for eons. In 2020, the confirmation went further still. NASA's Stratospheric Observatory for Infrared Astronomy, SOFIA, a modified Boeing 747, carrying a 2.5-meter telescope at 13 kilometers altitude, detected water molecules on the sunlit surface of the moon at Clavius crater, one of the largest craters visible from Earth. The detection was made at a wavelength of 6.1 micrometers, a spectral signature unique to water and impossible to confuse with hydroxyl, which had been the nagging ambiguity in earlier measurements. The concentration was low, roughly 100 to 400 parts per million, which is about 100 times less than the Sahara Desert contains. But it was there, on the sunlit surface, far from any permanently shadowed crater. The moon was wetter than anyone had imagined, and the water was not confined to the poles. The implications reshaped everything. Water on the moon is not just a scientific curiosity. It is the single most valuable resource for sustained human presence beyond Earth. Separate water into hydrogen and oxygen through electrolysis, and you have the two components of rocket propellant. A spacecraft refueled on the moon doesn't need to haul its return fuel from Earth, which means it can carry more payload, which means every subsequent mission becomes cheaper. The difference in cost between launching fuel from Earth's surface, climbing out of a gravity well that requires 9.4 kilometers per second of velocity to escape, and manufacturing fuel on the moon, where escape velocity is only 2.4 kilometers per second, is the difference between a program that limps along on occasional missions and a program that sustains continuous operations. Oxygen from lunar water is breathable. Water itself is drinkable. With a reliable supply of both, a lunar outpost becomes less like a remote Antarctic research station requiring constant resupply, and more like a settlement capable of partial self-sufficiency. The term the industry uses is in situ resource utilization, ISRU, and it has gone from a theoretical concept to the central pillar of every serious lunar architecture proposed in the last decade. But knowing the water is there and actually extracting it are separated by an engineering chasm that nobody has crossed. Start with the thermal environment. The permanently shadowed craters, where ice concentrates, are among the coldest natural environments in the solar system. Temperatures in the floors of craters, like Shackleton and Haworth, hover around 30 to 40 Kelvin, which is minus 233 to minus 243 degrees Celsius. For comparison, the average surface temperature on Pluto is about minus 229 degrees Celsius. These craters are colder than Pluto. Operating machinery in those conditions means every lubricant freezes, every seal contracts and cracks, every battery loses capacity, and every electronic component behaves unpredictably. Materials science for that temperature range exists in laboratory settings. Proven, flight-qualified hardware that can mine regolith in those conditions does not. The extraction process itself is no small matter either. The most commonly proposed method is thermal mining, which involves heating the regolith to release the trapped water as vapor, then capturing and condensing that vapor. Sounds straightforward on paper. In practice, you need to deliver energy to regolith in a vacuum at 40 Kelvin, collect gas molecules that want to scatter in every direction because there's no atmospheric pressure to contain them, transport the collected water to a processing facility, and do all of this with equipment that arrived on a rocket and was assembled by astronauts wearing pressurized suits and thick gloves. Every step introduces inefficiencies. Every piece of hardware must survive the thermal cycling between permanent shadow and sunlit areas. A swing of over 300 degrees Celsius across a distance of sometimes just a few hundred meters. And we don't even know what form the ice takes. That might sound like a minor detail, but it's actually one of the most important unknowns in the entire program. The ice could exist as solid sheets, buried under a layer of dry regolith, which would be the easiest to extract. It could be mixed into the soil grain by grain, like frost in frozen ground, which would require processing enormous volumes of material to recover useful quantities. It could be present as thin coatings on individual regolith particles, which would demand entirely different extraction chemistry. Or it could be some combination of all three, varying from crater to crater and meter to meter, until a rover or lander physically drills into the permanently shadowed regolith, measures what's there, and reports back. Every water extraction architecture is built on an assumption. NASA's Viper rover was originally designed to answer exactly this question. A golf cart-sized robot that would drive into the permanent shadows near the South Pole, drill up to a meter into the surface, and analyze the subsurface composition. In 2024, NASA canceled Viper due to cost overruns and schedule delays, even though the rover was nearly complete. The decision saved roughly $84 million. It also eliminated the only near-term mission specifically designed to ground truth, the ice deposits that the entire Artemis architecture depends on. That trade-off captures something essential about how the program operates. Short-term budget relief, purchased at the cost of long-term strategic knowledge. Now add the dust. Lunar regolith is not like Earth soil. It has never been weathered by wind or water, never had its sharp edges worn smooth. Every grain is a jagged, angular shard of rock and glass, many of them smaller than the width of a human hair. The particles carry an electrostatic charge because the lunar surface is constantly bombarded by solar ultraviolet radiation, which strips electrons from the outermost atoms of the regolith. Those charged particles cling to everything. They embed in fabric. They scratch optical surfaces. They work their way into mechanical joints. They abrade seals. During Apollo 17, Eugene Cernan reported that the dust infiltrated virtually every system it contacted. It coated the astronauts' suits so thoroughly that when they returned to the lunar module, the cabin filled with a sharp, metallic smell, the scent of freshly fractured rock, reacting with the oxygen in the pressurized environment. Harrison Schmitt, the mission's geologist, experienced nasal congestion and what he described as hay fever symptoms from breathing the fine particles. Their visors were scratched, their suit joints stiffened, and they were only on the surface for roughly 22 hours total. A sustained presence measured in weeks or months faces the dust problem on an entirely different scale. Every airlock cycle would introduce regolith into the habitat. Every EVA would grind it into suit components. Every rover would kick up clouds of particles that don't settle like they do on Earth, because there's no air resistance to slow them down. The particles follow ballistic trajectories and can travel remarkable distances. Without a solution for dust mitigation, a lunar base slowly abrades itself to death. NASA has funded research into electrostatic dust shields, surface coatings that repel charged particles, and airlock designs that minimize contamination. Some of these technologies show promise in laboratory conditions. none have been tested on the lunar surface. The gap between lab demonstration and operational deployment in one of the harshest environments in the solar system is not small. It is the gap where programs stall and timelines slip. Then there's radiation. The moon has no global magnetic field. It has effectively no atmosphere. Every square meter of the lunar surface is fully exposed to two distinct radiation threats. The first is galactic cosmic rays, high-energy particles originating from supernovae and other violent events throughout the galaxy. These particles carry enormous energy, some of them traveling at appreciable fractions of the speed of light, and they penetrate deeply into both spacecraft shielding and biological tissue. The damage they cause to DNA is cumulative and increases the long-term risk of cancer, cardiovascular disease, and neurological degradation. The second threat is solar particle events, sudden bursts of protons and heavier ions ejected by the sun during solar flares and coronal mass ejections. These events are sporadic and difficult to predict, with more than a few hours of warning. A major solar particle event can deliver a radiation dose that would be lethal to an unshielded human within hours. During Apollo, NASA monitored solar activity closely and chose launch windows during relatively quiet periods. The missions were also short. Most lunar surface stays were under 3 days. Statistically, they got lucky. No crew was on the surface during a significant event. Luck is not a viable radiation management strategy for a 6-month tour of duty. Shielding is the obvious answer, but shielding against galactic cosmic rays is fiendishly difficult because the particles are so energetic that they pass through conventional materials, and worse, generate secondary radiation when they interact with heavy atoms in the shielding. Aluminum, which is the standard structural material for spacecraft, actually creates more secondary radiation than it stops for certain GCR energies. The best passive shielding materials are those rich in hydrogen, water, polyethylene, or regolith itself, which means burying a habitat under several meters of lunar soil. That works for a permanent base. It does not help astronauts conducting EVAs on the surface, who would need to reach a sheltered location within minutes of a solar storm warning. Every serious lunar architecture now includes a radiation shelter, a heavily shielded room within the habitat where crew members can wait out a solar event. Some proposals use water walls, structural panels filled with liquid water that double as shielding. Others propose using regolith bags, essentially sandbags made of moon dirt, stacked over the habitat roof. The concepts are sound. The construction techniques for building such structures on the moon, with limited crew and limited equipment, are untested. There is also the question of what radiation does to the human body over time in ways we don't fully understand yet. Data from the International Space Station has given us a reasonable picture of low Earth orbit radiation exposure, where the Earth's magnetic field still provides partial protection. The lunar surface offers no such protection. The total radiation environment there is qualitatively different. Heavier ions, higher energies, no geomagnetic shielding, and the long-term biological effects of chronic exposure to that specific environment have never been studied in humans, because no human has ever lived in it. The Apollo astronauts spent at most 3 days on the surface. We're now talking about months. The gap in our medical knowledge is real, and filling it requires either extensive animal studies, which take years, or accepting the risk and sending people, which takes a different kind of courage than the one we celebrate in astronaut memoirs. What little long-term data we do have is not reassuring. A 2016 study published in Scientific Reports tracked the health outcomes of Apollo astronauts who flew beyond low Earth orbit, the only humans ever to leave the protection of Earth's magnetosphere. The sample size was painfully small. Only 24 people have ever made that trip, but the findings were striking. Apollo lunar astronauts showed cardiovascular disease mortality rates 4 to 5 times higher than astronauts who flew only in low Earth orbit, or who never flew at all. The researchers attributed this to deep space radiation, damaging the endothelial cells that line blood vessels, triggering chronic inflammation that accumulated over decades. 8 data points is not a robust epidemiological study. Nobody pretends it is. But it is the only human data that exists for the radiation environment we are now proposing to send people into for months at a time, and the signal it contains is concerning enough that it cannot be dismissed. On the International Space Station, astronauts receive roughly 150 millisieverts of radiation per 6-month tour, partially shielded by the Earth's magnetic field. On the lunar surface, estimates suggest exposure rates of 380 to 900 millisieverts per year, depending on solar activity. That is equivalent to 632 CT scans, or over 12,000 chest X-rays, in just 2 to 3 years. The biological effects of sustained exposure at those levels are modeled extensively, but measured in humans, almost not at all. We are designing habitats and mission durations based on computational predictions that have never been validated against real human physiology in that specific environment. The models may be right. They may also be wrong in ways that only become apparent after the crew comes home. All of this, the cold traps, the dust, the radiation, the economics, feeds into the central challenge of the Artemis program, which is not any single technical problem, but the sheer simultaneity of problems that must be solved at once. Artemis 2, the first crewed flight, will send 4 astronauts on a 10-day trip around the moon without landing. It has been delayed multiple times. The heat shield on Orion performed adequately during Artemis 1, but exhibited unexpected material loss, chunks of the ablative coating coming off in larger pieces than models predicted. The phenomenon, called ablation, is expected, but the specific pattern observed requires additional analysis before NASA is willing to put humans behind that same shield at lunar return speeds of over 40,000 kilometers per hour. When you're re-entering the atmosphere at 11 kilometers per second, and pieces of your heat shield are detaching in ways your thermal models didn't predict, caution is not bureaucratic timidity. It is survival. The heat shield issue is worth understanding in more detail because it illustrates how a seemingly small, technical anomaly can cascade into years of delay. Orion uses an AVCOAT ablative heat shield, a material that was originally developed for the Apollo program and then adapted for Orion with a different manufacturing process. During Apollo, AVCOAT was applied as a monolithic pore, filling a honeycomb substrate with a continuous layer of ablative material. For Orion, NASA initially switched to individually filled honeycomb cells, each one a separate block of AVCOAT bonded into the structure. The idea was to improve manufacturing consistency During Artemis 1, some of those blocks charred unevenly and detached in larger pieces than expected, exposing portions of the underlying structure to higher heat loads. The capsule survived, but the margins were thinner than the models predicted. NASA engineers spent months analyzing the char patterns, running arc jet tests on sample blocks, and building computational models to understand why the material behaved differently in flight than it did in ground testing. The answer, as best they could determine, involved complex interactions between the ablation gases, the boundary layer airflow, and the specific trajectory Orion flew. Interactions that ground testing couldn't fully replicate, because no ground facility can perfectly simulate the conditions of re-entry at 11 kilometers per second. The solution involved adjusting the re-entry trajectory for Artemis 2 to reduce the peak heating on the most vulnerable regions of the shield, a change that required revalidation of the entire entry, descent, and landing sequence. One anomaly, months of investigation, trajectory changes, revalidation, schedule slip. That's how spaceflight works. Artemis 3 is the landing mission, and its complexity is on a completely different level. The plan works like this. An SLS rocket launches from Kennedy Space Center, carrying the Orion capsule with a crew of astronauts. Separately, and this is the critical part, a SpaceX Starship configured as a lunar lander must already be waiting in a near rectilinear halo orbit around the Moon. Getting it there requires launching the Starship to Earth orbit, refueling it with multiple, possibly 10 to 15 tanker flights, using additional Starships, and then sending the fully fueled lander on a multi-day transit to lunar orbit. The crew in Orion docks with the Starship lander in lunar orbit. 2 astronauts transfer to the lander and descend to the surface, conduct their mission, ascend back to orbit, transfer back to Orion, and fly home. Count the links in that chain: an SLS launch, multiple Starship tanker launches, orbital docking and propellant transfer, a technology never demonstrated at this scale with cryogenic fluids, a translunar injection burn, autonomous orbital insertion at the Moon, crew rendezvous and docking in lunar orbit, crew transfer, descent, surface operations, ascent, another docking, another crew transfer, trans-Earth injection, re-entry. Every single link must work. A failure at any point grounds the mission. Think about what that depot operation actually looks like in practice. A Starship tanker launches from Boca Chica, reaches low Earth orbit in about 8 minutes, and immediately begins losing propellant. Liquid oxygen boils at minus 183 degrees Celsius. Liquid methane boils at minus 161. In the vacuum of space, with sunlight heating one side of the vehicle and radiative cooling chilling the other, the thermal management of 1,000 metric tons of cryogenic fluid is not a storage problem. It is a race. Every hour the propellant sits in orbit, a fraction of it warms past its boiling point, transitions to gas, and must either be vented overboard or actively recondensed using onboard refrigeration systems that themselves require power and add mass. The boil-off rate for liquid oxygen in an insulated but passively managed tank in low Earth orbit is estimated at roughly 0.1 to 0.5% per day, depending on tank design and sun exposure. That sounds small. Over the weeks required to launch, dock, and transfer propellant from 10 to 15 tanker flights, it compounds into a meaningful fraction of the total fuel budget. every tanker that launches must deliver not just the propellant needed for the lunar mission, but enough extra to replace what the depot has lost since the last delivery. The logistics of this cascade, choreographing more than a dozen launches within a tight window, docking each tanker to the depot without incident, transferring fluids through connections that must seal perfectly every time, and managing the thermal budget of the depot throughout, has no precedent in spaceflight history. The closest analogy is aerial refueling of military aircraft, which took decades to mature from a terrifying stunt into a routine operation. And that involves two vehicles flying through air, not two spacecraft floating in vacuum with cryogenic fluids sloshing inside them. SpaceX engineers have been working on this problem for years, and they are not naive about its difficulty. But solving it in testing is one thing. Solving it reliably enough to stake human lives on it is another. SpaceX operates on a philosophy of rapid iteration: build, test, fail, learn, rebuild, test again. This approach has produced extraordinary results. Falcon 9 is the most reliable and frequently launched rocket in the world. Its first stage lands and flies again routinely, a feat that was considered fantasy by most of the industry when SpaceX first proposed it. The company has earned the right to be taken seriously when it makes ambitious claims. Starship is the most ambitious claim yet, and it is progressing. Test flights have reached orbit. The booster has been caught by the launch tower's mechanical arms. Each flight demonstrates new capabilities. But the pace of Starship development and the pace of the Artemis program timeline exist in different temporal universes. Artemis moves at the speed of government procurement, congressional appropriation cycles, and multi-center coordination across NASA, ESA, the Canadian Space Agency, and the Japan Aerospace Exploration Agency. SpaceX moves at the speed of a private company with a singular decision-maker. Synchronizing these two timelines is a management challenge that may be harder than any of the engineering problems. There's also a landing problem specific to Starship that doesn't get enough attention. The lunar Starship is enormous. It stands roughly 50 meters tall, about the height of a 15-story building. During Apollo, the lunar module descended on a throttleable engine, and the astronauts could see the surface through their windows as they approached, picking out landmarks, adjusting their trajectory, choosing the safest patch of ground in the final seconds. The lunar Starship descends on multiple Raptor engines mounted high on the vehicle, far above the surface, with the crew cabin at the top. The astronauts would be roughly 50 meters above the ground at touchdown, looking down from a vantage point that offers a very different spatial awareness than Apollo provided. After landing, they need to descend from the crew cabin to the surface, either by an elevator built into the vehicle or by some other transfer system that hasn't been publicly detailed. Getting two astronauts in bulky pressure suits from the top of a 15-story structure to the lunar surface and back up again, repeatedly, without incident, is a design challenge that sounds simple until you actually start engineering it. In 1/6 gravity, with gloves that limit dexterity, on a timeline constrained by suit consumables. And there is the suit problem, which sounds trivial compared to rockets and orbital mechanics, but has become one of the most stubborn bottlenecks in the entire program. The spacesuits used during Apollo were engineering marvels for their era, but they were also deeply limited. They were stiff, restrictive, and exhausting to work in. Astronauts described the effort of closing their gloved fists as equivalent to squeezing a tennis ball continuously for hours. The suits were designed for short missions on relatively flat terrain, and they performed well within those parameters. What they could not do, and what the next generation of suits must do, is support sustained exploration across rugged terrain near the lunar South Pole, where the topography includes steep crater rims, permanently shadowed depressions, and boulder fields that Apollo never encountered because Apollo never went there. NASA spent over a decade and roughly $420 million developing the XEMU suit internally before concluding in 2022 that the program was behind schedule and transferring the contract to Axiom Space. Axiom's XEMU suit is designed to offer greater mobility, better dust resistance, and thermal management for the extreme conditions at the South Pole. The contract is worth approximately $3.5 billion across its full scope, and as of early 2026, the suits have not completed qualification testing for the lunar surface. You cannot land on the moon if your astronauts don't have suits to wear outside. This is the kind of problem that doesn't make headlines, but kills timelines. A rocket delay is dramatic. A suit delay is bureaucratic. Both stop the mission. And while NASA and SpaceX work through these challenges, China is executing. The Chinese National Space Administration does not operate under the constraints that shape the American program. There are no annual appropriation fights. There are no changes in direction every 4 years when a new administration arrives. There is no requirement to distribute contracts across congressional districts. The Chinese space program is a state priority backed by consistent funding, long-term planning, and a workforce that is growing rather than aging. The contrast in approach is visible in the hardware. China's Tiangong space station, completed in 2022, was assembled in roughly 2 years, using 3 modules launched on 3 rockets. For comparison, the International Space Station took over a decade to assemble across more than 30 launches by multiple nations. Tiangong is smaller, certainly, but the speed and reliability of its assembly demonstrated something that space analysts in Washington noticed immediately. China can execute complex programs on schedule. Chandrayaan and Chang'e. India and China. Both countries have demonstrated lunar capability in the last decade that would have been unthinkable 20 years ago. India's Chandrayaan, 3 successfully soft, landed a rover near the lunar South Pole in August 2023, making India the 4th country to achieve a controlled lunar landing and the first to land near the pole. China's Chang'e 5 returned 1.7 kilograms of lunar samples from Oceanus Procellarum in December 2020, the first lunar sample return mission since Luna 24 in 1976. The samples themselves produced a shock. Basalt rocks dated to roughly 2 billion years old, 1 billion years younger than any Apollo sample, meaning the moon was volcanically active far more recently than anyone expected. That single finding forced a rewrite of lunar thermal evolution models. Chang'e 6 returned samples from the far side of the moon in June 2024, a mission that required a relay satellite in a halo orbit around the Earth-Moon. L2 Point to maintain communications, a piece of infrastructure that China built and launched specifically for this purpose. that relay satellite, Queqiao 2, is still operational. It is available for future missions. It is infrastructure. And infrastructure is the difference between visiting a place and operating there. China has publicly announced plans for crewed lunar landings before 2030. The Long March 10 rocket, a new heavy lift vehicle designed specifically for lunar missions, is in development. A new crew spacecraft, larger than the Shenzhou capsule currently used for space station missions, is being built and tested. The International Lunar Research Station, initially robotic, but designed for the eventual human habitation, is planned for construction at the lunar South Pole, starting in the late 2020s. Russia is listed as a partner, though Russia's actual contribution, given its current economic and geopolitical situation, is uncertain. Other nations have expressed interest. Whether China's timeline holds is an open question. Space programs routinely slip. China's, while impressively disciplined, is not immune. But the pattern is harder to dismiss than the announcements alone might suggest. Every mission in the Chang'e series has succeeded. Every capability demonstrated was built upon in the next mission. The progression from orbiter to lander, to rover, to sample return, to far side sample return, to crewed landing follows a logic that is steady and visible. The geopolitical implications are not subtle, and they are shaping American space policy in ways that don't always get admitted publicly. The Outer Space Treaty of 1967, which both the United States and China have signed, prohibits any nation from claiming sovereignty over the moon or any celestial body. You cannot own the moon. You cannot plant a flag and declare a territory yours. But the treaty was written in an era when the question of lunar resource extraction was science fiction. It does not clearly address who has the right to mine lunar ice, process it, sell the resulting propellant, or control the infrastructure built around those operations. The Artemis Accords, a set of bilateral agreements initiated by the United States in 2020, attempt to establish norms for lunar activity, including the concept of safety zones around operational sites. As of now, over 40 countries have signed the accords. China and Russia have not. What this means in practice is that the first entity to establish a functioning, permanent presence at the lunar South Pole will have de facto influence over how resources in that region are accessed and used, regardless of what the legal framework says on paper. First mover advantage in the permanently shadowed craters, where the water ice is concentrated, is not just a scientific achievement. It is a strategic position, and both the United States and China understand this clearly. This is the undercurrent beneath the schedule anxiety around Artemis 3. The question is not just whether American astronauts will walk on the moon again. The question is whether they will walk there first, before Chinese astronauts do, and whether the infrastructure America builds will shape the norms of lunar activity for the next century. That pressure creates its own risks. Schedule pressure in human spaceflight has a documented history of producing catastrophe. Challenger launched in cold temperatures because of schedule pressure. Columbia's foam strike risk was normalized because of schedule pressure. Apollo 1's crew died in a fire caused partly by a rushed schedule that compressed safety reviews. Pushing Artemis to beat a geopolitical rival is exactly the kind of pressure that leads to cutting corners and the people at NASA who remember Challenger and Columbia know it. The tension between urgency and safety is not new in spaceflight. What's new is that the urgency has a specific competitor with a specific timeline, and that changes the calculation in ways that are uncomfortable for an agency whose institutional identity is built around doing things right, rather than doing them first. Apollo had the same pressure, of course, but Apollo operated in a different era of risk tolerance. The American public in 1969 was willing to accept astronaut deaths as tragic but acceptable. The American public in 2026 is not. So the program walks a tightrope. Move too slowly, and China gets there first. Move too fast, and someone dies. The optimal pace exists somewhere in between, and finding it requires a kind of managerial wisdom that doesn't always survive contact with political reality. Then there is the private sector, which has introduced an entirely new variable into the equation, one that didn't exist during Apollo or Constellation or the early SLS years. The Commercial Lunar Payload Services Program, CLPS, is NASA's attempt to outsource cargo delivery to the moon to private companies. Instead of building its own robotic landers, NASA buys rides. The agency selects payloads, instruments, experiments, technology demonstrations, and then contracts with private companies to build the lander, integrate the payloads, and deliver them to the surface. The idea is to stimulate a commercial lunar economy while giving NASA scientific data at a fraction of the cost of traditional missions. The results so far have been messy. Astrobotic's Peregrine lander, launched in January 2024, suffered a propulsion system failure that prevented it from reaching the lunar surface. Intuitive Machines' Odysseus lander, launched a month later, reached the moon but tipped over on landing, ending up on its side near the South Pole. It transmitted data for several days before its batteries died. A partial success in the most generous reading, a partial failure by any other. These outcomes were not entirely unexpected. NASA deliberately structured CLPS as a high-risk, high-reward program, accepting that some missions would fail in exchange for lower costs and faster iteration cycles. The agency's leadership has explicitly said they expect some CLPS missions to not survive landing. That acceptance of risk is philosophically sound, but practically complicated. Every failed lander delays the scientific measurements needed to plan human missions. Every failure feeds a narrative that the commercial approach isn't ready, and every delay in understanding the lunar South Pole's terrain, ice distribution, and dust properties makes Artemis 3's landing site selection harder, and the mission's risk greater. Intuitive Machines followed Odysseus with another attempt, and the company, along with Firefly Aerospace and several other CLPS providers, has continued to iterate on lander designs. The commercial lunar industry is genuine and growing, but it is also young, underfunded relative to the scale of the challenge, and still learning how hard it is to land softly on a world with no atmosphere to slow you down and a surface gravity just strong enough to make a bad landing fatal to the spacecraft. There is a deeper lesson in the CLPS struggles that connects back to the core argument of this entire story. Landing on the moon is hard. It was hard in 1969, and it is hard now. The absence of atmosphere means there is no parachute option, no aerodynamic braking, no margin for a shallow approach. You either fire your engines at exactly the right moment, burn exactly the right amount of fuel, and touch down at a survivable velocity, or you crash. The margin between a successful landing and a debris field is measured in seconds and meters per second. Apollo 11 came within 25 seconds of running out of fuel during its descent, with Neil Armstrong manually flying the lunar module past a boulder field that the automated guidance was steering them into. That was with the best pilots in human history at the controls, and it was still nearly a disaster. Autonomous landing systems have improved dramatically since 1969, but the fundamental physics haven't changed. The moon does not forgive small errors. Where does all of this leave us? The honest accounting goes something like this. We have a capsule, Orion, that works but is expensive and has a heat shield that needs more testing. We have a rocket, SLS, that works but is too expensive to fly frequently and is built on a political rather than engineering logic. We have a lander, Starship, that is the most ambitious spacecraft development in history and is progressing rapidly, but has not yet demonstrated orbital refueling, crew-rated reliability, or precision lunar landing. We have spacesuits from Axiom Space that are behind schedule and have not been tested in lunar conditions. We have a lunar gateway station, a small habitat in lunar orbit that is being built by international partners, but is not strictly required for the first landing, and has added complexity to an already complex architecture. We have a commercial lunar delivery ecosystem that is functional but fragile, with a track record measured in partial successes and instructive failures. We have all the pieces of a lunar program. What we don't have, not yet, is proof that all the pieces work together. And there is one more piece that almost never gets discussed, because it's not a spacecraft, or a rocket, or a spacesuit. It's the ground, specifically the Lunar Gateway. The Gateway is a small space station that will orbit the moon in a near rectilinear halo orbit, the same orbit where the Starship lander will wait for the Orion crew. It is being built as an international partnership, with NASA providing the power and propulsion element, and the habitation module, ESA, contributing the refueling and communications module, called eSprit. The Canadian Space Agency, building a robotic arm called Canadarm3, and the Japan Aerospace Exploration Agency, providing habitation components and life support. The first two modules are scheduled to launch together, though the date has slipped repeatedly. The Gateway is not strictly required for the first Artemis landing. NASA's own architecture shows that Artemis 3 can proceed without it, with Orion docking directly to the Starship lander. The Gateway becomes critical for later missions, Artemis 4 and beyond, where it serves as a staging point, a communications relay, and a habitat for crew members between surface stays. It also serves as the anchor for international participation. ESA, CSA, and JAXA contribute to the Gateway because it gives their astronauts a role in the lunar program, a seat at the table that they wouldn't have if Artemis relied solely on American hardware. The Gateway is as much a diplomatic instrument as a technical one. The risk is that the Gateway adds another layer of complexity to an already fragile schedule, another module to build, another launch to coordinate, another docking to execute. If the Gateway's first modules aren't ready when Artemis 4 needs them, the mission slips. If an international partner's contribution is delayed, everyone waits. The benefits of partnership, shared costs, shared expertise, political durability come with the inescapable cost of shared timelines. And underneath all of that, underneath the hardware and the budgets and the geopolitics, is a question that goes back to 1972. Does humanity actually have the sustained will to do this? Apollo lasted 8 years from JFK's speech to Armstrong's step. It was driven by a specific, measurable, externally imposed deadline. Beat the Soviets before the decade is out. When the deadline was met, the motivation evaporated. The program that followed, Skylab, was built from Apollo leftovers. The shuttle was a compromise vehicle designed to serve military, scientific, and commercial interests simultaneously, and ended up serving none of them optimally. The International Space Station took 30 years to assemble and cost NASA $3 to $4 billion a year just to maintain. Every post-Apollo program has struggled with the same fundamental challenge: sustaining political and public support for something expensive, risky, and slow, in a democracy that operates on 4-year election cycles and a culture that values immediate results. The moon doesn't care about election cycles. Building a sustainable lunar presence requires at least a decade of continuous investment after the first landing. The first landing is the easy part. Easy being relative, obviously. The hard part is landing again, and again, and again. Landing enough times to build infrastructure. Landing enough times that the supply chain becomes routine. Landing enough times that the cost curve bends downward as experience accumulates and reusable systems mature. Every time a new president takes office, the lunar program is at risk of redirection. Obama canceled Bush's Constellation. Trump created Artemis. Biden continued Artemis, but adjusted the timeline. Each transition costs months or years of momentum. Each one forces the program to defend its existence rather than advance its mission. NASA's annual budget in 2025 was roughly $25.4 billion. That sounds like an enormous amount of money until you consider what it covers: the International Space Station, Earth science satellites, the James Webb Space Telescope operations, Mars rovers, deep space probes, aeronautics research, technology development, education programs, and Artemis. The entire moon program competes for dollars with everything else NASA does, and everything else NASA does has its own congressional defenders, its own scientific community, its own public constituency. Artemis doesn't get $25 billion. It gets a fraction of it, spread across SLS, Orion, the Gateway, the Human Landing System, ground systems, spacesuits, and CLPS. Each piece is starving. The most optimistic scenario is that commercial involvement changes the dynamic. If SpaceX can make Starship fully reusable and drive the cost per kilogram to the moon down by an order of magnitude, the economics shift in favor of continuation regardless of political winds. If Blue Origin's Blue Moon lander, selected by NASA as a second source for Artemis lunar landings, provides competitive alternatives, redundancy reduces risk. If the Lunar Gateway enables international partners to invest in lunar infrastructure using their own funds and their own political mandates, the program becomes harder for any single government to cancel because multiple governments are invested. That's the optimistic scenario. The pessimistic scenario is that Artemis 3 slips past 2028, that China lands crew before the United States returns, that the American public reacts with a shrug rather than outrage, and that the next administration decides Mars is more exciting and redirects funding again. We've seen this movie before, 3 times. The pattern is so well established that aerospace veterans have a name for it. They call it the Lucy and the football problem, after the Peanuts comic strip, where Lucy always pulls the football away, just as Charlie Brown is about to kick it. The moon is always 10 years away, because we keep pulling the football. I want to be honest about something. The fact that we haven't been back to the moon in over 50 years is not primarily a failure of engineering. Engineers can solve the dust problem. They can solve the radiation problem. They can solve the thermal problem, and the refueling problem, and the landing problem. Given sufficient time and money, engineers solve everything. That is what engineers do. The failure is political. It is economic. It is cultural. It is a failure of sustained collective will in a society that is very good at sprinting and very bad at marathons. And yet, Orion has flown around the moon and come home. Starship has reached orbit. The Gateway's first modules are under construction in Turin and in Arizona. Astronauts are training for Artemis 2. China's Chang'e 7 is being prepared for a South Pole survey mission. India is developing Chandrayaan 4, a sample return mission. Japan, South Korea, and the UAE are all planning lunar landers. Private companies in at least 6 countries are building lunar payload delivery services. The amount of hardware pointed at the moon right now is greater than at any point since 1972. Something else is different too. Something harder to quantify than budgets and launch manifests. The conversation has changed. In the 1990s and 2000s, returning to the moon was discussed as a nostalgic exercise, a replay of Apollo for a new generation. That framing never generated enough political energy to survive a single budget cycle. The current conversation is different. It is about resources. It is about infrastructure. It is about the strategic implications of who controls access to the lunar South Pole and the water locked in its craters. It is about whether the moon becomes the fuel depot that opens the rest of the solar system, or remains a dead rock that we visited once and abandoned. That framing, resource-driven, competition-driven, infrastructure-driven, generates a different kind of political energy. It connects the moon to economic interests and national security interests in ways that pure science never could. Whether that energy is strong enough to sustain a multi-decade program through the inevitable setbacks, delays, and budget fights remains the open question. It has never been strong enough before. The track record is unambiguous, but the conditions have also never been exactly like this before, and dismissing the possibility of a different outcome because of past failures is its own kind of error. It's possible, genuinely possible, that this time is different, not because the engineering is easier, but because the economic case is stronger. Water changes the equation. Reusable rockets change the cost curve. International competition provides the urgency that domestic politics cannot sustain. Commercial investment provides funding streams that don't depend on appropriations committees. The alignment of technological capability, economic incentive, strategic motivation, and international momentum has never been this favorable. Or it could all collapse again. Another budget fight, another change in administration, another technical failure that pushes the timeline past the point where public patience holds. History says that's the likely outcome. History says the moon always wins the waiting game, but 53 years is a long time for a species that flew from Kitty Hawk to Tranquility Base in 66 years. Somewhere in that gap between what we did in 1969 and what we've failed to do since, something important about how we approach the hard things got lost. Not the technology, not the knowledge, something else. Something about being willing to commit to a goal that outlasts a single presidency, a single budget cycle, a single generation of engineers. The next footprint on the moon is coming. Every available indicator points to it. But it's worth being honest about why the last footprint took so long to follow. It wasn't the physics. It wasn't the distance. It wasn't even the money. Not really. Not in a country that spends more on air conditioning for military facilities than NASA's entire annual budget. It was us. It was the simple, frustrating, very human inability to keep doing a hard thing after the initial thrill wore off. We looked at the moon. We touched it. And we decided that touching it once was enough. The universe does not care about our attention span. The ice in those craters has been waiting for 4 billion years. It can wait a little longer. Whether we can is another question entirely. Thanks for watching, and I'll see you in the next one.